Greetings, the Astro 30 here yet again, and welcome back to AEL. Now, if you're new to this channel, please consider going down below and subscribing if you haven't done so already. Thank you very much. Today we're going to be looking at another exciting experimentation video using our old friend the 555 timer. Now, this circuit was published in Everyday Electronics magazine, August 1977, and it's an audio peak level indicator, or overload detector. And it's a very simple circuit. The 555 timer here is configured as monostable, where pin 2, the trigger input, needs to be less than 1/3 the supply voltage for its output state to go high. And we also have this common emitter class A transistor amplifier at the front end of it connected directly to pin 2. We have a collector load resistor here and a base biasing resistor here, so our output voltage at the collector here is going to be slightly higher than 1/3 the supply voltage. We can measure that, which is enough to keep pin 2 above the 1/3 the supply voltage threshold so it doesn't trigger. When the input signal comes in through either one of these sockets and they're looped back together so the input could come off the preamp and then this one can go back out to the power amp, for instance, going through this attenuator network, we can actually set the detect level, for want of a better term. So once the audio signal is at a sufficient amplitude for this transistor to start conducting, well, the collector voltage here will start to tend to fall close to zero as it's amplifying, which brings pin 2 below the 1/3 supply voltage required to trigger it, which will then cause pin 3 to go high, which will then cause the LED to turn on. However, there's just one problem. Audio is dynamic, so the transients are only going to be quick pulses. So it's not long enough visually for us to see that, oh, the light lit up. We want to incorporate a peak hold function so this LED stays illuminated for a short period of time, say 600 milliseconds. And that's where this RC network of R5 and C2 come in, connected to pins 7 and 6. This RC network here, with its current value, provides a delay time of roughly 600 milliseconds. So even if the input pulse disappears at pin 2, the LED will stay illuminated for around 600 milliseconds before the IC just resets, giving us enough time visually to see, oh, we're going into overload. And that's basically it. That's how the circuit works. There's nothing more to it than that. So what we need to do is build this up on breadboard, test it out, and see how well it works. Now, the problem I'm going to have is with a lot of the 1970s circuits that I've seen published, they seem to use the BC109 a lot. I don't have any. However, considering what this transistor is doing, a BC547 will suffice. We're not really looking for hi-fi quality here or good frequency response. All we want to do is, once the amplitude at the input is high enough for this transistor to conduct, is to bring pin 2 below the 1/3 the supply voltage threshold that is needed for it to go into a high state. So without further ado, let's build it up on breadboard and test it out. Yippee-ki-yay, mother. Well, a short time later I've got the circuit built and I've got I believe this is a 600 millicandela LED here, a fairly bright one anyway. Got a pot just off the screen here as a input attenuator, going through its 220k input resistor. Got the BC547 installed. Now, I had to make a substitution. I've got a 2.7 megaohm resistor here on the base instead of the 2.2 because I don't have one. This may be a problem, as it may bring the collector voltage down lower than 1/3 the supply voltage, which may be enough to trigger this 555 timer. So I might have to do a little bit of experimentation there. And the other substitution I've got is a 4.7 megaohm resistor here instead of the 5.6 megaohm in the RC network. All that's going to do is reduce the hold time from 600 milliseconds about to about 500 milliseconds, which is still long enough. And yes, I'm using the spotted 100 nanofarad capacitor, which there's nothing wrong with. So my supply is set to 12 volts, that should be 9. That may or may not be another issue, we'll soon find out. Got the current limited to 200 mA, so I'm going to apply the power, and nothing seems to have happened. Oh, wait a minute, the LED is on. So that's a slight problem. It shouldn't be. It could be that resistor is too high. I will measure the voltage at the collector in just a moment, but just to make sure, I'm going to reduce the voltage to 9 volts and see if that makes a difference. Nope, the LED is still permanently on. Okay, so that's a problem. Also, pin 5 has been left open. There really should be a 10 nanofarad bypass capacitor to ground just to keep the 555 timer stable. So, for sanity, before doing anything else, I'm going to install a 10 nanofarad capacitor between pin 5 and ground. So I'll just use this handy little capacitor, little wire there. And note, the LED is still on, so it's not a stability issue. Okay, so that's kind of pointless. I'll just turn it off and reset the circuit and see if that cured the problem. No, it didn't. Alright, so that was pointless. Alright, so I'm going to take the voltage back up to 12 and I'm going to measure the voltage at the collector. 3.75 volt, that is definitely less than 1/3 the supply voltage. 12 volts is the supply voltage, so half of that would be 6. So as we can see, that's like a quarter of the supply voltage, so it's too low. So that's triggering the 555 timer into its high state, as we can see there. So the only way I'm probably going to solve that issue is I'm going to take this 2.7 megaohm resistor out and I'm going to put two 1 megaohm resistors in series with each other to make 2 megaohm, which would be closer to the 2.2, and try again. Well, the two resistors are now in circuit in series, but it's actually made it worse. LED is on, however the voltage is even lower. So yeah, it needs to be a higher resistance by the looks of things, rather than a lower resistance. Alright, I've changed the resistor value to another 4.7 megaohm, just like the RC network, and now we've got more like 5 volts there, which is perfectly fine. That's above 1/3 of the supply voltage. So that's almost half the supply voltage, which is good enough. I don't know, however, if I'm going to change that to 9 volts and see the difference. Drops down to 3.9, which is again above 1/3 of the supply voltage, which is perfectly fine. So I'll bring that back up to 12. I don't know if the circuit's going to operate correctly now at that voltage. That may now have changed the input sensitivity. So if I disconnect them, see, all I've got to do is just gently touch the collector with the multimeter and it causes it to flip on and then go off. And as we can see with the RC network there, it's on for a satisfactory amount of time before it goes back out. So now I need to pump in an audio signal and see if I can get the circuit to trigger. Even just my finger on the input terminal is enough to trigger the circuit. I'll turn the potentiometer right down and it's still triggering it. Wow, that's sensitive. That's all the way down. Yeah, Christ. Alright, oscillator is connected, turned right down, and I'm currently running at 1 kilohertz. I'll just increase the amplitude of the oscillator. There it goes. And I'm just varying the amplitude pop back and forth. And the LED is on for a sufficient period of time to see it, so yeah. But the fact that I've got, I'll have to put this on a scope, that's where it triggers about there somewhere, come on. I need it to stay on. There it is. So that's with the oscillator up about halfway, but the pot's sitting around about 7 o'clock, so it's down near its minimum point of rotation. which probably means that input 220 kilo ohm resistor is probably too low as well. However, is that affected by supply voltage? So if I reduce this down to 9 volt, yeah, the LED just went out. Increase the oscillator again. Oh, it takes a lot more. I'm right up the maximum of my oscillator. I'm rotating the pot, and absolutely bugger all is happening. That's because I've turned the power supply off for some reason. Now, oh, there it is. So with the oscillator max, I can get that around about 9 o'clock. If it will ever go back out again. Probably not. So I've reduced the oscillator. Yeah, it's still pretty sensitive. So yeah, for detecting the peak on, say, a power amplifier, that input resistor needs to be a lot higher, because there's just not enough range on this pot. It'll be spending most of its time down near minimum. Okay, so I'm going to put the supply voltage back up to 12 volts. And I seem to have lost detection now. That's because that was rotated too low. Okay, so I'll bring this back up to where it stays on, which is about there, and I'll stick the oscillator onto the oscilloscope and we'll see what voltage is coming out of the oscillator. Okay, so there's a look at the oscilloscope screen. As we can see here, the yellow trace is what's coming off the oscillator, the blue trace is what's after the 220k resistor. Now we've got 554 millivolts RMS going in before, so the circuit is now triggered, and after the resistor what the base is seeing is 460 millivolts RMS. So that makes it fairly sensitive. However, where I'm measuring this output is after the resistor, it should really be after the pot, so we can actually see what's actually being seen by the base. So I'm going to walk around the camera tripod without kicking it, and I'm going to go at this capacitor. There we go. Well, now it's buggered off completely, so I need to increase that, and about 5 millivolts, mostly noise. Yeah, you can't even see it. So the resolution on my scope is not that great. If you wanted to use this on a power amplifier, you probably would want to turn this 220 kilo ohm resistor into a voltage divider, so that the voltage at this point, say if you've got 60 volt RMS coming in, you would want to bring that down to, what are we, less than about 500 odd millivolt. Then you'd have to make a calculation for that to make it work. However, in the interest of experimentation, I might stick in a ground reference resistor to make an attenuator, which will give the input more headroom. What can I put there? I'm not going to make it too sheer, probably 100k, just for testing. With the 100k resistor going to ground after the 220, we've got around 160 millivolts now, so we've reduced the signal strength by about a fifth. So if I wanted to reduce that even further, I would probably want to bring the 100k resistor's resistance value even lower. We know having a higher resistor going to ground is going to increase the voltage to the point where it's going to be the same as what's going in as what's coming out. So the resistance needs to be lower. So I'm going to test that theory. I'm going to stick a 47k in place of the 100k and see if that makes a difference. The 47k resistor is in, just under the probe here. And it did make a bit of difference, but not by much. It's now 113 millivolt. LED is off, and if I rotate the potentiometer, it comes on, goes off, comes on, stays on. Yeah, so we didn't get much benefit out of that. So let me try reducing the 47k to a 22. 22 is cobbled in there. See, this proves my theory. The lower the resistor value is going to ground, well, we get a greater reduction. We're now down at 65 millivolts. So my thought process there was correct. However, yeah, it's still, you know, if I increase that now on the input side till the light comes on and stays on, which it is now, we've got 715 millivolt coming in and 71 millivolt going out. So you could also increase the 220 to a higher value, such as 470 for instance, to allow you to connect it to an output of a power amp. However, I probably wouldn't, because it was obvious that this circuit was originally designed to be used on the output of a preamp, not a power amp. So yeah, that's going to be an issue if you want to connect to a power amp. You could, I mean, but the potentiometer that adjusts the sensitivity would be spending most of its time close to minimum resistance, which is okay, I guess, but it's kind of a pain in the ass at the same time. And in the interest of experimentation, I increased the value of that 220k resistor, oh that's noisy, to 470, and we didn't get much even more of a reduction there. It's now only about 35 millivolt. It only dropped off by about probably 12 millivolts. So yeah, so the circuit works, and it works okay, but it's not really, see, it's picking up noise from my hand. It's not really suited for power amplifiers, unfortunately. Not in this configuration. So it does work. I've proved that it works. Yeah, so the only modification that you would have to make is to increase this base biasing resistor to 4.7 megaohms instead of 2.2. This one can stay 4.7. The delay turn-off point is long enough to be able to see it. There's not that much difference between 600 milliseconds and 500, to be honest. So yeah, and maybe play around with the input circuitry here to include a attenuator, just to bring the input sensitivity voltage down. I mean, currently I'm about 9 o'clock and getting like 1.41 volt RMS going into the circuit. If that was dropped right down, well then it would take quite a fair bit more input voltage for it to trigger the circuit. Because if I turn that back down to just above minimum, the LED is currently off, so if I ramp the oscillator up and see what happens, well, I'm now at the maximum of my oscillator, which is about 6.79 volt RMS, and it's not enough to trigger the circuit. So obviously the pot is doing something. So if I gently, so I've only just given it a touch, and yeah, it's turned on. So, and I've just reduced the oscillator, it's turned off. So yeah, I'm going to say at the minimum position you need about 6 volt RMS in for that to trigger, and that's with the attenuator in circuit. So to finish this video, I'm going to draw up a quick schematic of what I've changed so we can see for clarity what's going on. So there it is, redrawn there. The only changes I've made, apart from this value being a little lower, that's fine, that's only the turn off delay constant. Everything else is the same except for this base biasing resistor is now 4.7 megaohm, and the inclusion of this attenuator, so 470k and 22k going to ground respectively. I'm also using a 100k linear pot here instead of the 47, which I don't have a 47k and they're harder to get. I also don't have a 50k. So the lower this resistance of this pot is, the more finer control and less time it's going to be spending in the lower portion of its rotation. So those are the changes. There's not much more else to explore with this circuit. Anyone else want to leave their thoughts below, feel free. But for now, I'm going to end this video here, and I may revisit this in the future. I'm not sure. There are other better ways of detecting peaks, including both the positive and negative going cycles, as being used as a clipping detector, for instance, by using an op-amp configured as a window comparator, is what it's known as, and it will detect both the positive going cycle and the negative going cycle and light the LED accordingly. I just called it a LED, didn't I? LED. Down you, Dave Jones. Anyway, that's it for this video. I'm the Astro 30, and if you enjoyed this video, please remember to go down below, like, comment and subscribe if you haven't done so already. And as always, this is the Astro 30 saying see ya, thanks for watching, have a great day.